we want to understand Bezrukavnikov's equivalence, which is an equivalence between constructible and coherent realizations of the affine Hecke algebra. And this is a categorification of the Kazhdan and Lusztig isomorphism between the affine Hecke algebra and equivariant K-theory of the Steinberg variety. And we need to be somewhat careful about how we categorify both sides. So the coherent sheaves on the Steinberg variety there, the first categorification you would guess is just to take, so to categorify K-theory, you just take coherent sheaves. This is a monoidal category. We won't quite do that, but the change is not so drastic on that side. But we also need to decide how we categorify the Hecke algebra. And this lecture will basically be about the long struggle that has gone over the last kind of 30 years to really nail down what the correct object is which categorifies the Hecke algebra in its constructible realization. So this is called A Hitchhiker's Guide to the Hecke category. And as usual, when I prepare these lectures, I kind of expected in one lecture to explain basically everything about the Hecke category, at least in broad terms. And then I got about halfway through and then I was already out of slides. So I want to, this is probably part one of a two-part series, but I won't probably give the second part next week. And very useful when you're going over this lecture is to have another look at lecture 16, sorry. So in lecture 16, I explained via examples the Grothendieck-Lefschetz fixed point theorem, how you can use a Tal cohomology to count points of algebraic varieties over FQ, and how this motivates Tal sheaves on varieties over FQ, and how we can get a function out of a sheaf. Okay, so please look at that lecture if those words don't mean so much to you at the moment. Okay, so we take X over FQ quasi-projective. And then we can consider the zeta function, which is given by some formula which you don't necessarily need to find comprehensible. It's just given by some power series. So this is the number of points of my variety over FQ to the M. I divide by M. And I multiply by Q to the minus MS. So e.g., for X is P1 over FQ, this is this zeta X of S is, so this is over M bigger than or equal to 0, X of some 1 plus Q to the M over M Q to the minus MS. And this actually, you can do a few lines of power series manipulations to see that this is 1 over 1 minus Q to the minus S times 1 over 1 Q to the minus 1 minus S. Do I have that right? Okay. I'm suspicious that this might be slightly wrong. Anyway, roughly speaking, That's what you get. And now we have the Weil conjectures. So this was, so you have to imagine that these numbers here are completely fascinating for arithmetic geometers. You put them into a power series, and then so this was something that people did motivated by the Zeta. So if you look in lecture, I think it's 6 maybe, I'm not sure, but I explained a long time ago in about lecture 6 what the zeta function of a number field is, and if you plug in the zeta function of a function field, you'll get this, basically this thing. Okay, so this has origins in number theory, but now we can define it for any quasi-projective variety over FQ. And what Weil noticed while I was in prison in World War II is that in various examples, this seems to have the following properties, which I'll just go over briefly. So rationality. That's the fact that this power series is actually a rational function, as we can see in the P1 example. Functional equation. And Riemann hypothesis. And roughly speaking, the functional equation is the fact that, so the rationality is the fact that you can write it as a rational function. The functional equation is something like zeta x of s is zeta x of 1 minus s. And the Riemann hypothesis is a statement about the zeros of these polynomials in some sense. So yeah, I mean, for an elliptic curve, you would write this as if E is an elliptic curve, this zeta E of S would be P0 of Q to the minus S, P2 of Q to the minus S over P1 of Q to the minus S. And so this would be 1 minus Q to the minus S. This would be 1 minus Q to the 1 minus S. And then this would be, this P1 would has 2 roots, both of norm Q to the half. And somehow that fact is the Riemann hypothesis for an elliptic curve. Okay. And then we have the Grothendieck-Lefschetz trace formula. Which says that the number of points of x over fq is the supertrace of Frobenius acting on the Étale cohomology of x. And this, it's a really nice exercise to get used to what the hell this formula means, is just to assume that there's some vector space and that this number is given by the trace of an operator on this vector space, and see how this expression miraculously simplifies and basically spits out the eigenvalues of your operator. Okay, so that's a nice way of understanding what the hell this thing means in hindsight. So this immediately implies the rationality, as you can check as an exercise. Poincare duality in étale cohomology explains the functional equation. And the Riemann hypothesis is explained by something called purity, which is so it's basically the statement that the eigenvalues of Frobenius acting in a particular cohomological degree of a smooth projective variety are of a special form. Okay. And I just want to note here, so so in order to define these cohomology groups, we need to change, we need to choose some auxiliary prime. So this is étale cohomology. And so no matter what prime that we choose that's not P, we get a cohomology theory and we get a whole lot of numbers out of it that don't depend on L. But in order to carry through this proof, we need to make this strange auxiliary proof. It's a strange auxiliary choice. And so this is a kind of shadow of the world of motives and things, and we'll see the same issue in the Hecke category. And I just want to say briefly that the proof of everything so if you think about how you prove something in algebraic topology, you kind of use a whole lot of long exact sequences and things like that. And so in order to develop long exact sequences and such techniques, we need the whole world of étale sheaves. And so that the proofs need so this is constructible. Étale sheaves plus the 6 functors. And the relative version of taking this this super trace of Frobenius led to the following. So the relative version of Grothendieck led to the fact that if I have an étale sheaf inside here, I can associate a family of functions, f to the m, and this is a function from the fqm valued points to ql bar. This is called trace of Frobenius. And a basic fact CF lecture 16 is that the Grothendieck group injects into the product of all these function spaces. Also, given any constructible étale sheaf, on a variety defined over SQ, I get a whole family of functions, and this whole family of functions determines the class of my sheaf in the Grothendieck group. And then this leads to Grothendieck's philosophy. Sometimes called Dictionnaire Fonction Faisceau. Which is that so there's this way out of a sheaf of producing a function, and the philosophy says that it should be easier to kind of, I don't know, one way of understanding the philosophy is that functions are there's just too many and there's too much flexibility, a bit like vector spaces are too flexible. But instead, if you regard them as representations or something, they become more rigid. And in the same way, functions are too flexible, but if we look at sheaves, then there's more rigidity. And we'll actually see examples of this in Masood's lectures, where so Laforgue uses this philosophy very heavily in order to establish parts of the Langlands correspondence for function fields. Okay. So this in some sense tells us what to do. Are there any questions about this brief review of? So another point of view that I learned from Professor Vilonen is there's another incarnation of this philosophy in which you replace sheaves by D modules, and you can interpret this correspondence as replacing a function by the set of differential equations that this function satisfies. And then you can expect that very interesting functions satisfy a lot of interesting differential equations. And so the kind of very interesting functions will be interesting D modules. For example, so the D modules that's kind of corresponding to the functions that satisfy the most differential equations are the so-called holonomic D modules. And so you expect the kind of interesting functions to give rise to holonomic D modules. That's another way of thinking about this dictionary. Okay, so this tells us to a rough extent how we should go about this. So Hecke category version 0. So I take G over FQ split, and this contains a Borel. And then I can also consider G K, where K is FQ. This is the loop group. And inside this, I can consider an Iwahori. And we've discussed several times now that the finite Hecke algebra is, I mean, what that is means, I'll go into in a little bit more detail in a second, is B of FQ times B of FQ bi-invariant functions on the FQ points of our group. So this is exactly an example where we've realized some algebra as the as the functions on the FQ points of a variety. And so we expect that this is categorified by some version of equivariant sheaves on G and the convolution. So this is basically what Grothendieck's philosophy tells us to expect. And H, the affine Hecke algebra, is the Iwahori bi-invariant functions. Whoops. On our loop group and the convolution. So we expect this to be categorified by I times I. GKQL bar. Okay. And just a remark, here I get immediately uncomfortable because this is very infinite dimensional. And so usually Iwahori equivariant sheaves on the affine flag variety. So where the affine flag variety is GK mod I is easier to work with. Okay, so, I mean, probably this is just a question of what you're comfortable with, but the issue is that GK is very infinite dimensional. Okay, the affine flag variety is infinite dimensional, but it's an in scheme. And so it's a union of finite dimensional things. Whereas this is a little bit too infinite dimensional for me. And what does this equals mean? It kind of means that we specialize, V is specialized to depending to something like this. So this thing is an algebra over a formal variable V, and when we specialize it, we get this algebra of functions. Okay, so now the rest of this lecture will basically be explaining why these objects are not quite right. And I want to proceed by kind of writing down a definition, and then seeing why it's wrong, and then changing, and then seeing why that's wrong, and then slowly converging to the right answer. So that's what the rest of the lecture will involve. So I just want to explain now what we would like to have. So please interrupt me if there are any questions.
So, Geordie, this is one particular specialization. So are there other specializations that are also interesting from the point of view of the things that we're talking about?
If there's other specializations of V?
Yeah.
Well, I guess there's the specialization V equals 1, which recovers the group algebra, which is, of course, very, very important. I guess also we're very interested in specializations at roots of unity. But yeah, there the geometric meaning is less clear, I would say. I didn't look who's here today, actually, so I'll just have a quick look. Hi, Joe. Okay, so what we would like to have. So I want to just recall that we have this Hecke algebra. So for simplicity, we concentrate on the finite case. So there's no essential difference with the affine case. So we concentrate on the finite case. i.e. for the Hecke algebra finite algorithm. So we have this Hecke algebra, and when we specialize V, we get this algebra of functions that we would like, that we want to understand. And here we have a kind of a Grothendieck inspired categorification of this. And here we have trace of Frobenius. And what we would like, we want an H such that, so the first is that H is monoidal and triangulated. And you can imagine the fact that, so this object is kind of independent of Q. Q is, so you just have this formal parameter V such that when you specialize it, you get all of these different versions. And so we would like H to be kind of independent of Q and L. Okay, so this comes back to this question in the Grothendieck-Lefschetz trace formula. We define this vector space that involves this auxiliary choice. We can prove the Weil conjectures, but why on earth do we need to make this auxiliary choice? And we would like it to fit in, so here, we would like H to sit here, and we would like a triangulated monoidal functor. Functor here. And we would like a map here, which is passage to Grothendieck group. Okay, in other words, we would like a canonical isomorphism of the Grothendieck group of H with HF. And I think that's all what we desire at present. And just a remark is that the existence So in Bezrukavnikov's equivalence, what we finally want to, so this should be the kind of finite version. We would like an affine version of this category. We would like this affine version to be equivalent to coherent sheaves on some Steinberg variety. But in the Steinberg variety, there's no Q and there's no L. So the existence of such an object. So if we had Bezrukavnikov's equivalence, then we could say, okay, this object is the other side of Bezrukavnikov's equivalence. So the existence of such an object is a prerequisite for okay. So now we try things and fail basically. And then after the fourth attempt, we get what we want. So, all good, this slide? I'm sorry. I'm exactly what I told others not to do the other day. Okay, so first try. And an instinct that we should have in all of this, whenever we write down a try, we should see what it is for the trivial group. Okay? The trivial group is a reductive group, so it should give something reasonable. So our first try will be to take H to be what Grothendieck roughly tells us to put down. And the problems the very obvious problem is that it depends on Q and L. But maybe we could imagine that actually this doesn't for some reason. And we could prove that. A more substantial objection is that for G equal the trivial group, then H would just be dB constructible on spec FQ. And this is continuous reps of pi1 étal of spec of FQ, which is Z hat. I mean, this embeds inside here on QL bar vector spaces, sorry. dB of this, and this has an enormous Grothendieck group. So for example, any, so an example of an object inside here is just to take QL bar with Frobenius acting by multiplication by any L-adic unit. So there's an enormous number of L-adic units. So this fails Grothendieck group test. So
Geordie,
I think, yeah.
Are you saying that this inclusion of derived categories is actually produces equality on growth in the group?
Yeah, so I think that this inclusion of derived categories, so I think that if you replace the right-hand side by all eigenvalues are L-adic units, then this becomes an equivalence. And so the Grothendieck group, like, is a free group on something like ZL bar star. Way too big. I don't think I had any other major objections to that one. So now we might think that the problem here is that we have the representation theory of this, this group already showing up on a point, and we can get rid of that by going to the algebraic closure. So maybe we should try and do that. Second try. Slide will disappear in 3, 2, 1 seconds. Perhaps we can, we could try H to be dB, B times B, G, QL bar, or Q. So here G is over FQ bar. Here G is over C with classical topology. So both of these attempts will be kind of wrong for the same reason. And so I can do it in the more comfortable version of the classical topology and explain why it's wrong there. So again, so this is rather nice because it doesn't appear to depend on Q or L. So the first objection's gone. But there's still an objection, which is that for G, the trivial group, H is just dB constructible of a point, which is just dB of finite dimensional vector spaces. And so the Grothendieck group is Z. And we want so the Grothendieck group is too small. Okay. But maybe this is just a stupid thing for the trivial group. And maybe this is the correct definition for SL2 or something. And so now I want to see that it's not the correct definition for SL2 either. B, so for SL2, the quadratic relation came from the fact that if we take the indicator function of SL2FQ and we convolve it with itself, we get 1 plus q times the indicator function of SL2FQ. Okay, and for this, CF lecture 16. And what's the kind of geometric explanation of where this 1 plus q comes from? So the convolution diagram, so this this kind of corresponds to the constant sheaf. And when we draw this convolution, so y, so what we draw is this convolution diagram, SL2 over B times SL2. And we have the multiplication map to SL2. And now this has a map to P1 times SL2, which sends GH to GB GH. And this 1 plus q here comes from, so if we take the constant sheaf here and push it forward, that's the same thing as taking the constant sheaf here and pushing it forward. And on functions, when we do that, what we do is we count the number of points in P1. So this 1 plus q comes from the number of points. So this should, I should say that this is the projection. Okay, so what this tells us is that if we take the constant sheaf on SL2 and convolve it with the constant sheaf on SL2, what we get is the cohomology of P1 tensored with the constant sheaf on SL2. So this is, so by this I mean, this is a graded vector space here. And so this is isomorphic to Q SL2 plus Q SL2 in degree 2. And so now exercise. Is that if we consider the Grothendieck group of our purported Hecke category, we just work out in the complex numbers. So this is isomorphic to the group algebra of W of Z mod 2Z, where S goes to the class of the constant sheaf on SL2 minus the class of the constant sheaf on the skyscraper, minus the class of this constant. Okay. So now we really are convinced that the Grothendieck group is too small. And moreover, you can see, so this tells us that the constant sheaf, if I square it, I get 2 times the constant sheaf on SL2 in the Grothendieck group. And this 2 should somehow become a 1 plus q. And that looks suspiciously like we need to take weights into account. We want to replace an Euler characteristic, which is 2, the Euler characteristic of P1, with 1 plus q, which is more like the trace of Frobenius. So the moral is somehow weights into account. Okay, so maybe I'll just do the third try and then we'll have a break. So we'll have third try number 1, third try number 2, and then fourth try will be successful. So we're up to third try number 1. Any questions so far?
I have a question. Yeah, so what do you, right here, what do you mean by the FQ points of Iwahori?
So the, like GK of FQ. So this is some group scheme or group in scheme or something, such that when I plug in FQ, I get G of FQ T. And this group scheme has a, or in scheme has a sub scheme. So this is all over FQ, such that I of FQ is what we would usually think of as being the points of the Iwahori.
How do you define I as a group scheme then?
I mean, you know, how do you define this guy?
I don't know.
You know, it takes some work. You know, like roughly speaking, you can think about this thing that like, for example, let's think about this on Lie algebras. Like what are the FQ points of the Lie algebra of this thing? You have, like, for every coordinate in your group, you have power series many coordinates in FQ. For every entry in your group. And now for the Iwahori, you're just saying that certain of these entries are 0. And so that's a closed sub-scheme of this massive thing.
That helps a bit, I think.
I mean, like, probably a good example to think about is like, you know, for G equals GM, then GK of FQ FQT, and then inside this IK of FQ would be FQ T. Okay, I think we should have a break now. So the third try is again, we take G over FQ. And we could maybe think, oh, the Grothendieck group was too big last time. Let's just disallow a whole lot of stuff in the group. So take a full subcategory. And so we can take H to be the subcategory generated by the intersection cohomology complexes. And there's two important points here that I need to explain. The first thing is what I mean. What do I mean by? And so this is all Tate twists. And what do I mean by Tate twist? So if we look at, so what is Tate twist? So if I look at the compactly supported Étale cohomology of A1, this is just QL bar with Frobenius acting as multiplication by Q. And this thing gives us an Étale sheaf on a point and then we define for F in DBC XQL bar set F of M to be F tensored with P upper star of Q L minus 1. So basically these the power, so this object is invertible and its tensor powers give us Z many different objects on a point, which are tensor powers of the Tate object on a point. And tensoring with these objects gives us a way of changing Frobenius weights in a simple way. We basically just we modify the Frobenius weights by multiplying them by a factor of by a power of Q. And a kind of technical point, which I don't think I'll go into too much, is that in the Hecke algebra, it's useful to have a square root of Q. We already saw that in the formula when I was saying V specializes to 1 over the square root of Q. It's convenient to have this parameter V. And this means that we, and this kind of categorifies to the fact that it's useful to have a square root of this Tate object this can be constructed either formally. It's possible just to add a square root of this object to your category in a formal way, or in the Étale setting, by choosing a square root of Q. Okay, so perhaps we should say half Z instead of Z here, using this square root of the take twist in order to do so. Okay, so that's the first point that I needed to explain here. The second point is that this is, so it's highly non-trivial that this category is closed under convolution.
So Geordie, what do other subscripts mean? There was a bunch of subscripts.
Sure, I'll just so, oh, sorry. So this means closure under shift. This means triangulated. And this means convolution. So yeah, so the good point. So if I add the convolution there, it's absolutely obvious that it's closed under convolution because it is so by definition. Thanks, Masood. But even if I do this definition, then it's still closed under convolution. And that's very non-trivial. Okay, so just for the, basically, so let me explain why this is non-trivial. So the first statement is that the convolution of two intersection cohomology complexes is a direct sum of shifts of intersection cohomology complexes. So after base change to the algebraic closure, this is the decomposition theorem. But we want to know that this is true before. So already the decomposition theorem is non-trivial. So we're using a very big theorem in order to say this is closed under convolution. But we're actually using more. We're saying that before we go to the algebraic closure, these things lie inside this category. And roughly speaking, that means that when we convolve, the only weights that show up are powers of our Tate object. So
Geordie, I have a stupid question. So here you're allowing somehow all shifts, right?
Mm-hmm.
And all Tate twists. But this ICX itself sort of naturally lies on some shift. I mean, I'm just wondering why we're allowing everything as opposed to sort of try to carefully, or is that hopeless to try to pick, some shifts and some Tate twists?
Yeah, I think it's hopeless to. So what you could say is kind of inside this would have a subcategory of things that are pure of weight 0. And this would be preserved. But my suspicion would be that this would be the only thing that you could do that would, and later we'll see this subcategory of things of pure of weight 0. But once you kind of deviate from that a little bit, then you'll get everything. Okay. So I just want to give, so I just said verbally why this is non-trivial, because I think that if the non-triviality of this means something to you, then you already know enough. But just accept this if that's more challenging. But now we're in good shape. So if G is the trivial group, then this version of the Hecke category, let's call it third attempt, is the full triangulated subcategory of QL bar sheaves on a point whose weights are of the form m over 2. And the Grothendieck group. So this is the triangulated category generated by these things, is ZV V inverse, and V corresponds to this half-take twist object, let's say. And for general G, the Grothendieck group of the third attempt is the Hecke, Hecke algebra. Okay, but we still have a little issue in that this is not obviously independent of P and L, Q and L. And I just want to give an alternative version of the third try. So in order to motivate this, I just want to recall a picture that I feel is useful. So we have the Weil conjectures. And these gave rise to the Frobenius action on a Tal cohomology. So in order to solve the Weil conjectures, we would like a vector space with an action of something such that the trace of this operator gives the number of points. And in order to establish the properties of this, we developed the theory of Tal QL bar sheaves. Now on the other side of this, so this is for X over FQ. But there's an alternative kind of universe in which very similar ideas make sense, which is X over C, where we have Hodge theory. And then there's this philosophy, so there's Grothendieck's theory of weights. And in order to articulate Grothendieck's theory of weights for varieties over C, Deligne came up with the theory of mixed Hodge structures. And then in order to fully understand what's going on with mixed Hodge structures, we kind of need the analog of Étale QL bar sheaves, and this is Saito's mixed Hodge modules. And then there should be some kind of ephemeral world of motives up here, which kind of, so these very complicated theories should be incarnations of a more universal theory, which is motives. And somehow we can see the definition that I just gave is the Hecke category realization in this world. But we can also ask, does it have a realization in this world? And in asking that question, we kind of realize something interesting about the Hecke category, which I want to explain now. So the third try, number 2, would be to do H to be the same thing, but inside the world of mixed Hodge modules. So X in WF. So we do the same thing. We do all shifts, all sums, and shifts, take twists. And here there's really no option. We have to do this take twist as being a formal thing, half take twist as being a formal thing, and triangulated inside dB b times b of mixed Hodge modules. And this also has correct Grothendieck group. Okay, so yeah, so now the fact that it's closed under convolution is just the decomposition theorem for in the setting of mixed Hodge modules. And I just want to go over very briefly a subtlety. And again, we see this subtlety already for a point. So are there questions? I'll move to the next slide. So the subtlety is the following. So just so that we don't lose direction. So we kind of want this Hecke category to be a kind of universal thing. And so if we can write down two different incarnations, one in the Étale world and one in the Hodge module world, we would like this thing to be able to go to both of them. And there's a very important difference between the world of mixed Hodge modules and the world of Étale sheaves that's already visible on a point. So for G a point, for G trivial, the X groups between take twists are really different in the two worlds. So, the kind of H Étale and H mixed Hodge modules are different. And it's somehow not, it's not an aesthetic difference, like it's a really fundamental difference. So if we compute X groups, X1 from one of these to a shift of itself, so this is in a tile world. So this is QL bar. If M is equal to 0. So this is just the fact that you can have Jordan blocks. So this is the kind of, this is basically the same thing as representations of the integers, and the integers, if two eigenvalues are the same, if the eigenvalue is the same, then it's an extension, and if the eigenvalue is not, then there's not Jordan block. So in mixed Hodge structures, so these mixed Hodge structures are the mixed Hodge modules on a point. So yeah, so this is the saying that same weights extend. Different weights don't. In mixed Hodge structures, it's kind of the opposite way around, that X1, so I would need to be more precise about exactly what version of mixed Hodge structures I'm using, if I'm using real mixed Hodge structures or mixed Hodge structures or complex mixed Hodge structures. In mixed Hodge structures, there's no extensions between objects of the same weight. But different weights do extend. And the final remark is that under Bezrukavnikov's equivalence, I said at the start of last lecture that we expect the kind of action of Frobenius, so this very non-trivial kind of weight grading, to just to correspond to a C star action. So the upshot is that there should just be no X on a point. Okay, so what I'm saying is that in one incarnation, you have X between things of the same weight. In a different incarnation, you have X of things of a different weight. And both of these answers are wrong, and you should have no X whatsoever. So in the notes, I discuss a historical incarnation of this issue. I'm not sure how much. Maybe it's worthwhile. I still have 20 minutes or so, so I'll go over this briefly, this historical incarnation. Can someone tell me either this makes no sense or it makes some sense?
So Geordie, can you just quickly remind us what these categories over points are? So the L-adic one is you're looking at representations of Z hat, where one goes to some L-adic unit, and then you also include some twists. And the mixed Hodge one, how do we think about that over a point?
So in the so in the L-adic one, if we just look at all L-adic sheaves on a point, then this is basically what you just said. But then we say, oh, there's way too many of these. So we just consider those representations in which Frobenius acts by a power of Q or maybe a power of square root of Q. And roughly speaking, so this is almost what we want, except for the fact that there's nothing that tells us that Frobenius might act semi-simply, that has to act semi-simply. And that's the issue in the étale world. And that's exactly where this nasty X comes from. We have Frobenius acting in a non-semi-simple way. And one can kind of explain why that is really bad for us. So there's a very famous conjecture, which is that the Frobenius should act semi-simply on the étale cohomology of any smooth projective algebraic variety. And this in fact implies that the Frobenius will act semi-simply on the étale cohomology of any quasi-projective variety. And so even though we can write down such étale sheaves, they should never occur in nature. They are not of, if we find the correct world of motives, then such things will never show up. Okay, so that's the étale world. In mixed Hodge structures, what we are basically saying is that we're only allowing Tate twists, which is kind of saying that you're only allowing the very simplest Hodge structures imaginable. Like, for example, cohomology of cell-stratified varieties and things like that. So we can never have Hodge numbers that aren't PP, and there's no interesting structure there. Does that make sense, Masood?
Yes. Maybe later in one of the lunch things we can discuss what is mixed Hodge on a point more, but we can skip it now.
So the following is probably a very useful way of thinking about it. So this category is, so if we forget about the square root of Tate twists, so we just look at Tate twists, and if we're looking at complex mixed Hodge structures, then this is a finite dimensional graded vector space together with a nilpotent endomorphism of degree 1, of degree 1, or 1 or 2, depending on how you normalize. Okay, so let's say that this is to be discussed at lunch. But so you can think about this as being some reasonably explicit linear algebraic objects. Okay, so I just want to do a tiny bit of historical incarnation of this issue. So this is kind of, as far as I'm aware, the first time in our mathematical development where this issue became apparent, is that if we take the principal block of category O, then this is equivalent by valence and Bernstein localization to certain D modules. And then this becomes equivalent to B constructible perverse sheaves on the flag variety. So this means B constructible. And this means the complex flag variety. And so this is one of our lovely affine cell stratified varieties that we saw was highest weight a few weeks ago. Now, general nonsense tells us, so this is a finite length abelian category with finitely many simples. And so general nonsense tells us that this is equivalent to finitely generated modules over some algebra A. So A is a and what Zergel showed in around about 1990 is that A has a grading and if I look at finitely generated graded modules, this provides a grading on the principal block and explains Q in Kazhdan and Lusztig polynomials. So the Kazhdan and Lusztig conjecture said that certain fundamental multiplicities in here are given by the value at 1 of some inductively defined polynomial. And so then you're like, why the hell is this the value at 1 of a polynomial? And what Zergel tells you is that there's actually some nicer category. So let's call this O0 tilde. So now this is a graded category. And if we look at the now graded multiplicities in this category, then we recover Kazhdan and Lusztig polynomials and not their values at 1. And so we have this category. So this is O. And now a very fundamental question at this stage is, what is the geometric meaning of O tilde? And I'm sure that many people at the time, you know, thought they were very clever and said, oh, you know, that's just mixed perverse sheaves. Okay. Or that's just mixed Hodge modules. But it is not. And it's slightly different. And that's what BGS explained. So, okay, so BGS explained that A tilde is defined over Q. Well, this was already known to Zergel. Over Q. And if we look at A tilde QL bar modules, graded, this is equivalent to some geometric category. Which is related, but not exactly the same as perverse, which is related to dB, B of G mod B, QL bar, where now G is over FQ. And such that A tilde C graded modules is equivalent to some geometric category, which is related to DBB, of mixed Hodge modules on G mod B, where this is the complex flag variety. But the relation in each case is subtle, and it involves some cooking to remove the problematic X from earlier. Okay, so in this case, you would like some category in which that Jordan block is forbidden. And here you would like some category in which the non-trivial X's between things of different weight on a point are forbidden. Okay? And in each case, the way that you do this is different. Okay, and I'll just say, so there's recent motivic versions due to Zergel and Wendt. And Zergel, Wendt and Werk do this without any cooking. Okay, so the moral is that if you work in an appropriate category of motives, the cooking is already built into the motives and everything works. Okay. So now I'll finally get to the fourth try, which will be successful. And this fourth try is somewhat ad hoc in the sense that we write down a definition and then prove that it works. And I have no doubt that this is the correct object, but we probably don't yet have the correct definition of that object. Okay, so fourth try. So first we define a category which will play the role of the objects which are pure of weight 0. So this is just in the classical topology. So this is a much more elementary object. We're not using Hodge modules or anything. All we're taking is intersection cohomology complexes and taking the full additive category that they generate. And note that this is not triangulated. It's just an additive category. And now we do something very weird, which was we redefine. So what we're about to do is take the homotopy category of this additive category. And the homotopy category has a shift as a complex, which we want to denote by square brackets. But this category here already has a shift. And so we call the shift on this category by a different notation. So we redefine shift by 1 to be homological shift on H semi-simple. And note that by decomposition theorem. And now our definition is to take the homotopy category of this guy. And note that on this has two different structures. It has the internal shift, which if I imagine this as complexes of objects of HSS, this is the thing that doesn't change it just shifts every element of this complex term by term. So this is the shift in HSS. And it also has the shift by one. So this is the shift in the homotopy category. And again, I hope that we've learned that we should always work out what we get for the trivial group. HSS, so this is just the additive category of all shifts of intersection cohomology complexes on a point. So IC on a point is just a trivial vector space. And so this is just dB C of a point, which is just dB of finite dimensional vector spaces. But now we're not viewing this as a triangulated category. We're just viewing it as an additive category. And so as additive categories, this is just equivalent to finite dimensional graded vector spaces. Okay, so now H is KB of finite dimensional. And note that the Grothendieck group of H is indeed ZVV, the inverse, and V corresponds to shift of grading. So 2 remarks and then I'll finish. Sorry if I went too fast there. The Grothendieck group of H is the same thing as the Grothendieck group of the Hecke algebra. 2, a similar definition over FQ bar with QL bar sheaves leads to an equivalent category after and the proof is by showing that in fact all of these objects have another combinatorial description in terms of Zergel bimodules. So we show that this H semi-simple is equivalent as monoidal categories to Zergel bimodules. And then the last thing is that with some difficulty, which suggests that this is still not the right. So as I said before, I think this is the right object, but it's not entirely clear that it's the right definition yet. And one of the reasons that it's clear that it's not the right definition is that you can construct kind of realization functors to these approximations with difficulty, but it's not easy. One can construct to their to the Étale versions and to the module versions, and then this has, by construction, this guy has okay. So the upshot is that H does the job. Okay. And so in a later lecture at some point in the future, I will explain this connection. But next week, I'll go back to the next steps towards Bezrukavnikov's equivalence. And yeah, I hope that this lecture has given you some idea of the kind of subtleties involved in the Hecke category and what to watch out for. And so, yeah, most of the time in the Bezrukavnikov world we'll be working in some kind of variant here in the Étale setting. But yeah, in order to get everything at the end of the day, we'll need to move back to here. So thank you, and as normal, I will be around for a few minutes in case anyone wants to ask any questions. And otherwise, see you soon.
I just have one question.
Sure.
So in the affine, so in the affine case, you do the same thing.
Mm-hmm.
So they are the circle bimodules in the affine case, and you can use them, or
yeah.
Okay. Thanks.
But I guess you still sort of want a loop realization of the affine Hecke algebra. Oh, sorry, of the affine Hecke category. I mean,
yeah,
you know,
so that's an excellent question.
Presentation.
So that's what Leonardo Maltoni should be doing, but it's really unclear. I mean, there's lots of difficulties in making that work. In some sense, the loop realization is Bezrukavnikov's equivalence.
Mm-hmm.
Yeah, I mean, I would claim that if so, the constructible version of the Hecke category is very naturally the Iwahori presentation, whereas on the other side, coherent sheaves on the Steinberg or whatever, that's very naturally the loop presentation. You know, you have generators corresponding to finite simple roots, and you have lattice given by line bundles.
Yeah, I guess I was thinking more of just the fact that I mean, even in the Iwahori presentation, you're visibly working with geometric objects which are loopy, which are, you know, the group in schemes are derived from the original finite dimensional algebraic groups by looping. You know, if you just consider the affine Weil group as purely as a Coxeter group, it's it doesn't feel like it's looping so much. I mean, I
totally agree, but I would kind of argue that the Iwahori presentation is more naturally associated to the Coxeter presentation, and the loop presentation is more naturally associated to the loopiness.
Yeah. Okay, there might be enough loopiness. So one question I had about this last slide is whether you talked about realization functors from this version of H to the Étale and mixed Hodge versions of H.
Mm-hmm.
Are those really monoidal functors in any sense?
Yes. So
Um,
they're monoidal. These
so
are
it's-
monoidal functors between monoidal triangulated categories.
okay. It seems like quite a strong statement about convolution on in the
Yeah,
sheet.
so it's this statement that I was making before that things are kind of semi-simple before extension of scalars to the algebraic closure.
Mhm.
Which is, you know, takes like many, many pages of work to show.
So, Geordie, I thought you were going to say something about the X matching up at the end, because the third try didn't work because of the X. And so now the claim is that the fourth try, the X do work, right?
Yes, so that was in some sense like, so I hope the moral from the third try was that we can do it in two different ways, and on a point we get different, like really different X's, which suggests that if we want any object that maps to both of them, we just need no X whatsoever on a point. That was what the third try was meant to tell us. And that's meant to be this statement. Okay. Now we're in this wonderful world, like the homotopy category of graded vector spaces is fantastic because we have no X whatsoever. Which is kind of meant to be the push out of no X between things of the same weight and no X between things of different weights.